Good morning to you all. I am Aman Kumar Jha from IEM Kolkata. I am going to present a paper on triple time, an encryption algorithm with time factor and variable block size. So in this paper, cryptography, I am working on cryptography. Cryptography is a technique which offers us a way to transfer the confidential data in presence of intruders. It includes the two processes, encryption and decryption. Cryptographic algorithms are of two types, symmetric algorithms and asymmetric key algorithms. Now I am working on symmetric key algorithms. In symmetric key algorithms, there are three major barriers to modern encryption standards. The first one is permanent collision of ciphertext. In this collision, same plain text encrypted with same key gives the same ciphertext at different system time. Most of the encryption standards that we follow these days are like these algorithms. The second one is fixed block size. Suppose you want to increase the security, so you have only one choice to increase the security, that is to increase the key length. There is no any chance of increasing the block size. If we can design an algorithm in which the block size is flexible according to the security level requirement, then it will be a major milestone in the symmetric key algorithms. The third one is algorithm dependent key. The key designed for one algorithm cannot be used for others. So if we can make the key independent of each other, then it will be great, as keys are very different from other files and can be easily detected. Therefore, if the keys detection we want to nullify, then we have to design an algorithm which is independent of the key or its type. The key can be media files, image files, or anything else. Now, in my algorithms, there are various stages. I am going to elaborate these stages in next parts. The first part is preparation for encryption. In this part, at first we initialize P boxes and S boxes. Then we extract the current system times and store it in a variable say randomizer. Then we store the randomizer with the block size maintainer. Block size maintainer is nothing but a variable derived from the size of the block which we have received from the user. Suppose user want to encrypt using a size of 9 bytes, then block size maintainer will be calculated from that, and then that will be stored with the randomizer. So see here, randomizer is dependent on time and on the block size. That is, if we can merge the randomizer in our encryption, then our encryption will be time dependent and block size dependent. This is the time factor which is going to be used in my algorithm. Now, at first we merge the key into P boxes and S boxes. This will make the P boxes and S boxes key dependent, and key dependent P boxes and S boxes are much more secure than any other. Now, merging is done with XOR and add operation alternatively for each key byte. That is, first key byte is XORed and second key byte is added, and like this. These merging are done alternatively. In P box, first XOR, then add, then again XOR, then add. And in S box, first key byte is added, the next key byte is XORed, and so on. All additions in the key are mod 256 format. XOR all P boxes and S boxes with randomizer. See here, all the P boxes and S boxes are now time dependent, key dependent, and block size dependent. Now here comes the main function triple time, for which the algorithm is named triple time. This is a very complex function, and I am going to briefly describe it. So first step is the first byte of character set. Suppose any argument character set is passed to this function triple time, then the first byte of that character set is converted to its equivalent binary form. We are going to use this function again and again, so it is important to understand it. The binary form is flipped horizontally using parity bit. The binary form is expanded from 8 bits to 9 bits. 8 bits is already an ASCII format, and we are going to extend it to 9 bits. Now we will arrange these bits into a 3×3 row measure matrix. Now we transpose the matrix, and bits are extracted from the matrix considering row measure order and arranged in a linear form. Now a variable column index is calculated from the first 5 alternate bits of this extracted part. Another variable row index is calculated from remaining 4 alternate bits. That is, for a number, suppose a binary number 1100101111, the first 5 alternate bits will be 10111 and 1001. Here column index will be 10111, which is equivalent to 23, and the row index will be 1001, which is equivalent to 9 in decimal format. The data present as S boxes with column index and the data present in the S box with column index and row index as its indices is extracted first and stored in a blank array variable, say set I. Now I is increased by 1. Now next byte of character set is extracted, and step 1 is executed again until the entire character set gets operated. Now here comes the step 3. I is set to 0 if direction bit, which is a bit which will be passed to the triple time function by the user or by the programmer. The programmer passes the direction bits according to the algorithm, and if direction bit is set to 0, then set I, that is shifted to the left by 1 bit and then stored with the next set, that is set I plus 1, and then stored in a array variable, say character set. If the direction bit is set to 1, then the same operation is done in a reverse manner, that is set I plus 1 is shifted to the right by 1 bit and then stored with set I, and the stored value get stored in character set I. Now increase I by 1. Now here comes the step 4. Step 3 is repeated until set I plus 1 exists. As soon as I becomes equal to 1/3 block size minus 1, that is the last element of the set I, then the character set is defined at set 0 stored with set 1/3 block size minus 1, that is the last character set is defined as first set, that is set 0 stored last set. Now entire character set is returned by the function. This is the triple time function which will be used in our algorithm. Now here comes the preparation of plain text. The first block of plain text is splitted into 3 equal blocks, say L is splitted up into 3 equal blocks, say L, M and R for the leftmost, middle and rightmost set respectively. Now here you can see that left part is stored with right part, and it is now new right part. Again middle part of the old set is stored with right part of the old set, and it is the new left part, and middle part itself remain unchanged for the next middle part. Now iteration say I is set to 1. Here in the diagram you can see T3. T3 is the triple time function, which is very complex function as I explained earlier. Here L, M and R is operated with different P boxes as shown. Here you can see that the leftmost, middle and rightmost are first passed with triple time function and then stored with the corresponding P boxes. You can assume that the merging with P boxes not only makes it P boxes dependent, but also makes it time dependent and block size dependent. Here you can see the R is merged with L after passing from the T3 function, and it is then merged with P box, and then it is the new M part. Similarly L is merged, that is stored with P boxes I star 3 minus 3, and it is the new left part, and right part is formed from storing the middle part and right part passed from T3 function, and then storing with P box I star 3 minus 1. Now this is the step 1. This is repeated. Here you can see the step 1 is shown in the diagram, and this whole step is repeated until all S boxes get used up. That is total 96 iterations. Now after all these iterations, there are 3 remaining P boxes. We store the 3 remaining P boxes with the 3 blocks L, M and R respectively. Now join the resultant formed side by side to form the ciphertext. Now put the ciphertext into ciphertext file and extract the next plaintext and repeat the same encryption process and so on until entire plaintext get encrypted. Put ciphertext into ciphertext file and then extract new plaintext and repeat the same encryption process, so on until and unless entire plaintext files get encrypted. Now store time factor with block size again. This will nullify the effect of block size stored previously. Why we have done this? The reason is because we want to place the randomizer in the ciphertext file. So, we calculate a position based on weighted value of key file and put time factor in ciphertext file at calculated positions. Now, calculate a position based on a weighted value of key file, extract the time factor from. Now, here goes the decryption process. For the decryption process, calculate a position based on weighted value of key file, extract time factor from the ciphertext file from the calculated position. Now, XOR time factor with the block size. Preparation for decryption remains same as preparation for encryption. Ciphertext is extracted and split up as before. XOR last 3 p boxes with 3 blocks L, M and R consecutively. Set iteration I to 96. LMR are operated with p boxes as shown in the diagram. This is the reverse diagram of the ith operation of encryption. This is the reverse diagram, so it is in decryption. Here you can see at first we merge the L, M and R to the corresponding p boxes to which it was XORed earlier. Then we passed it to the triple time function. Here you can see it is something like a very complex algorithm. Now, in step 2, step 1 is repeated until all S boxes gets used up, that is up to I equal to 1. Now, 3 parts again are processed as shown in the diagram. Here it is the reverse diagram for preparation of encryption. L, M, R are just simply joined side by side to form plain text. This plain text is placed in the plain text file. Finalizing decryption. This is an important step. Here extract new next ciphertext. Repeat the same decryption process. The above 2 steps continues until entire ciphertext file gets decrypted. Now, here comes the experimental analysis. Here you can see that there is a graph between variation in ciphertext and time in millisecond. Variation of slope in our proposal. This slope justifies that on various different amount of time, the ciphertext file get altered. This verifies that the same plain text encrypted with same key gives different ciphertext at different system time. The ciphertext can have 256 different variation in a single millisecond. Breaking of block integrity. Here is the come for scope for future development. What can be done in future? Here you can see the breaking of block integrity. The block integrity is defined as, suppose we encrypt the first block of plain text, then it is compulsory that this will be saved as first block of ciphertext. If we can break this integrity, that is, suppose we encrypt first block of plain text and it gets saved as third block of ciphertext, then it will be a major milestone in the field of symmetric key algorithms. Now, the second thing which can be done in future is that merging time factor in block fragmentation. That is, after doing all this, we merge time factor in that unique identification of time factor. Suppose we merge date, time, year, hour, second, millisecond, then it will be unique for each and every moment of time, and it will be a unique identification. So, it will make our algorithm more stronger. In addition, we can merge hash into our algorithm for in future. The conclusion is, in my algorithm, we can see the p boxes and s boxes are key dependent, p boxes and s boxes are time dependent, block size is flexible, key size is also flexible, p boxes and s boxes are block size dependent, and key is algorithm dependent. So, here we can see this is a lot more good algorithm, more better algorithm than DES, Blowfish or other algorithms like in which some of them are either not key dependent, many of them are not time dependent. I have found a very few algorithms which are time dependent, but they are at a small scale, not a very large scale, and so on. So, at last, thank you for hearing me so patiently.